Well, hello. Today we're going to be talking about work, energy, and power. Work is the energy transferred when a force is applied to an object through a distance d. What I want you to know here is that it says work is equal to a parallel force to the distance. And what that means is that the force and distance have to be in the same direction. If they're in different directions, then work isn't being done. It's actually something different called moment. But for right now, we're going to talk about work. So the force and the distance, the force is in the same direction as the distance, or we would say they're parallel to each other. The other thing I want to point out to you is down here at the bottom we talk about the units. And the units for work or energy, any type of energy, is joules. 1 joule equals 1 Newton meter. And we say 1 Newton meter because force is measured in newtons, distance is measured in meters. So that would be 1 Newton meter, or a joule. Here's an example then. Student lifts a 50-pound ball 4 feet in 5 seconds. How many joules of work did the student complete? Well, as you can see, you take 50 pounds times 4 feet and you get 20 foot-pounds. This is the amount of work, but it's not in the SI unit of joules. We can't say it's 20 joules because we're using feet and pounds here. Now what we've got here then is a conversion. We can convert 50 pounds into newtons by taking it, basically dividing it by 0.225 pounds. There are 0.225 pounds per newton. And then 4 feet is 1.2 meters, 22 meters. And we basically, there are 3.28 feet per meter. So we would take this 4 feet and divide it by 3.28. If you multiply these two then to find the work, what you're going to get then is 271.5 joules. Now my J is a little bit ugly over there, but it is supposed to be joules. Well, things I want you to get from this is that energy is the ability to do work. If you have energy, then you're going to be able to do work. And what that means, if you have energy, you can apply a force for a certain amount of distance. If you're running out of energy, you will not be able to either supply a force or to be able to push that force for a distance. So either A, you'll have zero force, or you'll have zero distance. Forms of energy, well, there's potential energy. Usually it's stored energy, often referring to gravitational potential energy, but it could be chemical energy like gasoline as well. Kinetic energy, this is energy in motion. Can be anything it's moving, whether it's a turbine, whether it's a helicopter blade, whether it's a space shuttle taking off, whether it's at a dam. These are all different forms of kinetic energy. Energy transformation. Every day we take chemical energy as we eat, convert it into motion as we move. Take radiant energy from the sun. It can be turned into chemical energy, and we turn it into different forms of chemicals, and it changes. Electrical energy can be changed into thermal energy. So this energy transformation is always constantly happening one way or the other, and there's really a lot of different ways that could happen. Renewable energy sources. All right, we've already talked about these to a certain extent. We have non-renewable energy sources, and we've talked about those to a certain extent. What I want to talk about here then is conservation of energy. Energy cannot be created or destroyed, but it can change from one form to another. So, as we said earlier, let me find it up here, we just talked about it. Alright, I'm losing it already. Here we go. Energy can be transformed, but it can't be lost. So I'm just going to throw some numbers up here because sometimes that's easy to remember. If we take in 100 joules of food, then we can transfer this energy into 100 joules worth of kinetic energy. If we have 100 joules worth of electric energy, then we can transform it into 100 joules of thermal energy. It's not going to be lost. It's going to be transformed there. And that's what this conservation of energy means. It can't be destroyed or lost. Energy, sometimes we say, is lost to heat. Like we lost heat, or we had friction. We didn't really lose any heat, or we didn't lose any energy. It was just transformed into a different form. So, for example, even though we might take in 100 joules of food, we may not get 100 joules of kinetic energy. This maybe is how much we took in food. And we got maybe, let's say, 75 joules of kinetic energy, motion, playing whatever we did, but we also had body temperature raised. So we probably got 25 joules then of thermal energy. That's what I'm going to use, TE here. So it was conserved. It wasn't lost. It was just in a different form of energy that maybe we weren't able to make use of. But it was not lost. It still was just transformed to a different type. Here we go through all different types of examples of energy conversion. I will take a look at that. But here in our vehicles, we take gasoline, which is a chemical energy. Some of it goes into mechanical, and some of it goes into heat, just like the food. The chemical energy is the food. Part of it goes into turning the wheels, and that's the mechanical energy. Part of it comes out the exhaust and the heat. Well, which output is desired, the mechanical or the heat? Well, obviously the mechanical is what's desired there. We don't want to be losing energy. Ideally, we wouldn't be losing energy out the exhaust system. Efficiency. Efficiency is the percentage of the input energy that is transformed to output energy in the desired form, E out. So this is nothing different than what we did earlier in the trimester when we were talking about work input, work output. And the reason it's still the same is, remember, energy is work. All right, this is work output, work input. It's the same thing here. All right. So energy and work are the same. What are the current energy concerns? Well, as you can see here, U.S. energy consumption by source. Biomass is only 2.9, hydropower 2.7, geothermal 0.3%, wind 0.1%, solar another 0.1%. Petroleum, 38%. Natural gas, 23% essentially. Coal, basically 23%. Notice that the three main energy consumptions that we're taking up by source are all non-renewable, and that's what our concern is at what point are these no longer existing? What point can we no longer count on these? Alright, power. Power is the rate at which energy is expended or work, W, is performed in time T. In my ICP class, I quite often talk about, let's dig a trench, 1 foot deep, 1 foot wide, all the way across the classroom. One student gets it done in an hour, the other student gets it done in 5 hours. The student who gets it done in an hour did not do more work. The work they did was the same. The difference now is the power. How fast do they get it done? Because power, unlike work, takes time into its equation. In our equation for work, there is no, trying to find it up here real quick for us, there is no time taken into consideration here. So power is the first time that we've actually been able to take time or make time part of our conversions or part of our factor here. So how fast are we doing this work is what power is. And the units for this are watt. 1 watt is equal to 1 joule per second. Energy is in joules, time is in seconds, so watts are equal to joules over seconds. Now, types of power. We have electrical power. Notice I've got an equation. We won't talk much about this, but it is going to be a part of your lab. Power equals I times V. I obviously is current. V is voltage, but that right there will be a large part of our lab. Make sure you're ready to work with that. Mechanical power. Well, this is work divided by time. We've just talked about that. These two right there are what's going to be used in your lab. Fluid power is typically going to be work divided by time, but it's energy transferred by liquids. Power example. All right. Student lifts a 50-pound ball 4 feet in 5 seconds. How many watts of power did the student use to lift the ball? Well, earlier in the problem, earlier in our notes, we had found out that it was 271, I believe 0.5 joules, but they've left it here as 271 joules. So that right there is our work. And the time now is 5 seconds. Earlier in our notes, we didn't take this time into consideration. Now we're going to. Well, if you take 271 and divide it by the time, the 5 seconds, we get 54.3 joules per second. And of course, a joule per second is a watt. So we get 54.3 watts. Well, hey, that's going to be it for today. I'll see you on the flip side.